Okay, now let's proceed with non-ideal solution. So non-ideal solution that we know we have two graphs. One is positive deviation, another one is negative deviation. Okay, normally at low concentration of solute, most solution shows deviation from ideality. Either it will deviate from ideal behavior of Root's law. Alright, either it will deviate in positive way or negative way. So let's look. Alright, so positive deviation, normally volume of solution is more than volume of the component. Delta H solution is positive. Example like water ethanol mixture. Okay, negative deviation. Volume of the solution is less than volume of the pure solution. Delta H solution is negative. This is fine. Okay, what you need to understand is this one. This is really crucial. Okay. Alright, so for positive deviation, you have to know positive is a smiley graph. Okay, smiley graph is smile, negative deviation, okay, negative graph. So there is a sour graph. Alright, you unsmile. Right, so for positive deviation, total vapor pressure of the solution of two miscible liquid is higher than calculated. Boiling point is lower. That's why the graph is smiley, because of this boiling point is at the lowest part. Okay, and then this graph is the negative graph because of boiling point is the highest part. Okay, and then as we know, as I mentioned before, in fractional distillation will produce distillate or residue. Okay, distillate is the one that we want, residue is the one that left from the distillation. So what is distillate, what is residue to determine? So we have to know there are only two things that we are going to be produced. Either one is azeotropic mixture or pure liquid. So who will come first? Azeotropic mixture normally is located near to this dot. Okay, this dot, this point. Okay, but pure liquid is far from it. Alright, so we look at the first one. Alright, okay, first thing first, you have the graph of temperature versus solution. This graph shows that at this region contain of pure A, at this region contain of pure B. So meaning that this graph high reach of pure B at here. Let's say B is benzene, A is ethanol, for example. Okay, it doesn't matter. Right, so what happened here? First thing first, we're going to heat up the solution from X point. Okay, at this point, this could be around 60%, around 40%. It depends on from where we read the graph. If we read from here to here, so this would be 100%. Okay, this would be 0%, for example. Okay, but the other way around, if you read the graph from the other way around. Okay, from now I read it from, let's say, left to right. So X is around, let's say I have here around 70% of pure B. It's not 100%, just 70 for, let's say. So what happened here, the concept of distillation. Okay, we heat it up. When it reach the point, the curve is going to bounce in the curve. Okay, it's going to bounce in the curve until it found another curve. Okay, so this is the region where equilibrium between vapor and liquid. Okay, so this is liquid region down here, this is vapor region all here. Okay, so this is the equilibrium between vapor and liquid. All right. Okay, so now when it reaches this region, it's going to bounce down. It's going to melt. Okay, it's going to what we call melting. Okay, so yes, all right. So what you have, you're going to produce a number of component here. All right, let's say Y. Okay, so how many Y that you produce here? Let's say this is 70, this is 50. Yes, the process could be a reverse process. Okay, it's fine. So now we have to determine who is our distillate, who is our residue based on this graph. So you have to look at what is your endpoint. Endpoint U is at this part. Okay, before it's coming down. Okay, so it reached at this part. Okay, this end. Okay, so means that this end is near to the point of azeotropic mixture. Okay, as I said, dot in the middle Okay, in the middle where the dot is, that is called azeotropic mixture. So means that our distillate, the first one that coming off is distillate, because residue is always at the back. Okay, second thing that's coming out. So our distillate here is azeotropic mixture because it's near to this dot, and then our residue must be the pure liquid. Okay, there's only two things that will come out, either azeotropic or pure liquid. So our pure liquid, who is our pure liquid? Pure liquid is pure liquid of A or B. Okay, alright, so now look at this one. Look at this graph. This is graph of negative deviation. The same thing, we have pure A, we have pure B. So this is a reach of B. Okay, this is a reach of B. Right, so we have a maximum temperature, this one temperature, second temperature, and third temperature. Okay, so how to read it? From Y, you heat up, it's going to vaporize, liquid going to vaporize until it reach the point. Alright, and then at this point it's going to produce equilibrium between vapor and liquid until it reach this point. Alright, so once at this point it's going to condense. It's going to condense until here. Okay, what you produce this point of X at this point. So let's say around 25%, 10% like that, right? So now you have to determine who is your distillate, who is your residue. You have to see the end product. This is where the last point of the end product touch the curve, okay? Okay, so now when we have this point, we have to bring it here. Okay, so means that that's going to determine who is our distillate. First come off is distillate. Who is our distillate? Distillate is pure A because it's near to the A region. Okay, so that's mean pure liquid A. Alright. Okay. Alright. And then who is our residue? Residue is second one that coming off because of azeotropic mixture is number 2 that is coming off. Okay, and it's far from distillate just now, so our residue is azeotropic mixture. Okay, so this is the thing, properties that you have to memorize about positive deviation and negative deviation. Okay, azeotropic mixture, this is the explanation. Alright, the liquid mixture that deviate widely from ideally cannot be separated completely by fractional distillation. That's why azeotropic mixture is mixture with constant boiling point where the vapor is the same of composition of the liquid. That's why it has the point where it's like that. Okay, point there are constant here. Okay, alright, so fractional distillation yield from one liquid component and azeotropic mixture. Okay, alright, that's fine, you can read that. Okay, look at this one, positive deviation. Again, the graph is small. Okay, this is the negative deviation, the graph is sour. To this, okay, if I want to reverse the graph, you can put a graph of propanol as topic. So meanings that, okay, if you put propanol, X of propanol, you want to say that this is reach of propanol, right? Okay, so this is start with 0. 0 is here, 0.36 is here, 0.36, and then it's hard for me to draw. Okay, 0.36. And then the rest is 0.64. So 0.36 temperature is around 56 here, and then 64 here, 61.2, 64 around here. So graph U should be like this, for example. Right? Okay, this is two things. Alright. Okay, this is how we draw the graph. Okay, so I want you to determine who is azeotropic, who is distillate, who is residue, who is distillate, who is residue. Okay, for both graph, I want you to draw both graph. One is propanol as topic, one is trichloromethane as topic, and then determine who is distillate, who is the residue. For this one, who is the distillate, who is the residue. Okay, so we will discuss in the lecture. Right, so I want you to do the same for number 2, number 3, number 4, and number 5, and then we discuss. Okay. Okay, next is water alcohol system. This is the same thing. Okay, so let's say from 20% we heat it up. From the liquid it's going to vaporize at 90 degrees. It's going to equilibrium between vapor and liquid until it reach point E, and then it condense to point F, and then it being heat up again. Alright, so this is because it goes down here, condense here to produce some percent of methanol, and then it being heat up again. Okay, and then equilibrium again to the G, and then G we're going to condense, produce more methanol here, and then from methanol we're going to heat up again until this point. Alright, so the concept of fractional distillation, and then when it reach this point it coming down, so means that in the end we're going to have more rich of methanol. Okay, alright, so the same thing, concept of distillation. Yeah, we have seen it before. I have explained before the same thing. You heat it up, and it reach water, it's going to condense, and then it's going to produce distillate over there. And then it being heat up again. So heat up, equilibrium when it reach this point, vapor and water. Alright, liquid and vapor, equilibrium, and then it being heat up again, equilibrium, heat up again, equilibrium until you reach the end point. Okay. Right. Okay, now it's about eutectic. Eutectic is a mixture of two or more phase of component at lowest melting point. This is not look at on boiling point. We look at a melting point. Alright. Right. So eutectic graph is like this. Okay, eutectic phase diagram describe behavior of alloy to component which is completely soluble in liquid water. Right. You can look at here. We have A, we have B. So we have reach of region B here. This is region A. Okay, so you are given temperature, you plot temperature 1, temperature 2, temperature 3, and then you draw the graph just like that. Okay, graph normally be straight line, is okay. Alright, so this is region of A and B. Alright, what is it? We'll look at later on. This is L and B. Okay, L could be liquid. Okay, and then L and A, because A and B is the mixture. Okay, mixture of the melting. So this region consists of liquid and B region, while this region consists of liquid and A region. Okay, right. Okay, eutectic point is point on the phase diagram where the maximum number of allowable phase are equilibrium. When it reach, the temperature must remain constant until the phase disappear. Okay. Alright. Okay, so look at this one. Okay, how to draw eutectic graph? So let's say you have percentage of cadmium. When you have percentage, this means the highest one is 100. Okay, so this is 0. Okay, let's say we read from here to here. Right, so means that this is the region of cadmium. Alright. So, and then this is the region of another one. Let's see, what is it, another one? Zinc. Okay, zinc. So, in order to draw the graph, you have to look at where is the temperature of cadmium given. The pure liquid of zinc is cool and it's freeze at 419. Zinc, this is the region of zinc. So, the highest temperature is 419 degrees and then it melted. So, this is going to melt. This is the highest and then it's going to melt. The amount of cadmium is added to zinc and heated up to liquid. Okay, that's fine. And then it says here, adding more cadmium causes freezing point to drop until finally at 270. Okay, finally, this is the lowest temperature that is going to melt. Right, so you have to draw a line like this. Right, and then put dots itu like E, alright, and then that says 270. And then it says pure cadmium is freeze at 3.3 to 1. Okay, cadmium this region, so you mark here 3 to 1 is slightly lower than 419. So you mark like that. So that's it, your graph is finished. So just draw the line here and the line from here to here. So you are done, right? So if you're going to name the phase, this is liquid phase. Okay, always liquid phase, and then whatever here is a solid. Okay, in this case we have actually the mixture of zinc and cadmium. Okay, zinc plus cadmium. Kenapa dia solid? Because it's been melted. Okay, sorry. Okay, this is graph of eutectic. Is a graph of freezing. Okay, from liquid it's going to freeze. Alright, not melted, it's going to freeze. Okay, so zinc and cadmium is this region. So this region contain of, because it's near to cadmium, so cadmium plus liquid. This region is near to zinc, so zinc plus liquid. So means that whatever you have inside here is at equilibrium. Whatever you have here is at equilibrium as well. This is the equilibrium region. This is the liquid region. This is the zinc and cadmium region. Okay.